Okay, guys, we are moving to section 2.9, some special second order equations. Well, in this chapter 2, we are mostly doing first order equations, right? But there are some second order equations which can be reduced to first order equation by using special substitutions, and we are going to cover them. In the book, in section 2.9, mostly they explain theory which is not related to special equations of second order. So they have this like theory about this somewhere else, like in the homework part of the section. So I'm calling it 2.9, but actually there is a very little part of 2.9 which is dedicated to some special second order equations. Okay, so we are going to consider two types. Type number one is going to be equations with dependent variable missing. What does it mean? Dependent variable missing means that there is no y. No y. I'm going to give you an example. So it's going to look like this. Second derivative equals function of t and y prime. There is no y in this equation. Missing y. Well, how do we solve it? Method. Substitute v equals y prime. Well, what is going to happen to y2 prime then? Well, we just differentiate this expression and we get v prime equals y2 prime, so v prime. And how our equation is going to look, instead of second derivative, we are going to have first derivative of v, and the function is going to be of t and v. The only one little advice, do not forget that you are doing substitution and go back to y. Otherwise, it's going to become equation of first order, which we probably will be able to solve very easily. So example number 1. T square y second derivative plus 2t y first derivative minus 1 equals 0. You see there is no y here. That's a second derivative, first derivative, but no y itself. So we are going to substitute v equals y prime. So we are going to have t square v prime, because it's a second derivative, right? Plus 2t v minus 1 equals to 0. And we are going to recognize that this is exact equation. Let me write it down. Move this 1 to the right side. T square v prime plus 2t v equals 1. How do I know that this is actually, or you can fit an integrating factor. Mu equals, or it's not actually integrating factor. We don't need the integrating factor here. That's not mu equals, but it's exact equation. It's already kind of the derivative. So I don't know. Well, I'm going to write down mu equals 1 actually. So this 1 is a derivative of t square v. Do you see it? You differentiate t square v. First, you differentiate v, copy t square v, copy t square, and then you differentiate t square, and that's going to be 2t v. Actually, I think this is one of the examples we had in the integrating factor section. Well, very easy to integrate, right? I'm going to integrate left and right side. And I'm going to get t square v on this side, right? I'm going to put dt here and dt here, so it looks better. And t plus a constant here. Now I just need to solve for v, right? And v is going to be t plus a constant over t square. I'm going to simplify it a little bit, dividing by t square both sides, t and both terms, t square. Now that's not my final solution. And actually, getting to this part is easy. Finding y is going to be difficult. I remember that v is actually y prime, right? So I'm going to copy y prime instead of v. I'm going to write down v equals y prime equals 1 over t plus c over t square. And How do we solve it from this point? From this point, we just integrate it. Y prime equals to this function, so what is y? I'm finding antiderivative. Integrate y prime dt, and integrate this 1 over t plus c over t squared dt. Well, here derivative and integral kind of cancel each other, right? On this side, we have a ln of t instead of this, right? And minus c over t, power function. And because it's integral, we are supposed to have another constant. But this constant and this constant are different. So I'm going to label this number 1 and this number 2. So there are two constants. Why? Because equation of a second order, right? So we have two constants. Well, very good. We solved it. Now I think I'm going to suggest you to solve something on your own. I'm going to give you an equation and ask you to solve it yourself. So try to do it. I'm going to count to 3 and provide you with a solution, but my suggestion, while like if you got the method is not difficult, right? Try to do it on your own for 5 minutes. So I'll start counting. 1, 2, 3. Solution. Well, as usually, substitution v equals y prime is going to turn my equation into first derivative of v plus t v squared equals 0, which is separable equation, right? I'm going to have dv over v squared. I'm separating the left side and right side, and this one is dv dt, right? Or d. And on this side, I have minus t dt. Well, integrating both sides is going to give me negative 1 over v, right? A power function. And on this side, minus t squared over 2 plus a constant. Yeah. So what should I do next? Oh, well, maybe find v, because my goal is actually to find y, right? So I'll need to solve it for v. What I'm going to do, I'm going to multiply it by negative 1 and write it out like this. 1 over v t squared over 2 plus a constant. Why do I have a constant? Positive. Because constant is arbitrary number. Minus arbitrary number or plus arbitrary number, still arbitrary number. Now I'm solving for v. I'll need to flip this part over. It's 1 over t squared over 2 plus a constant. Before I start solving this equation, I'm going to multiply both numerator and denominator by 2. I'm going to write it like this. 2t squared, 2 here, plus a constant again. Wow, what happens to the constant? Why it never changes? It's supposed to be 2, right? Well, 2 constants is still a constant, so it's kind of new constant, but I still can call it a constant. Okay, are we done? No, guys, not yet. V is not our function, right? Our function is y, and v is a derivative. Remember that v is actually y prime. So we'll need to substitute back. Y prime equals 2 over t squared plus a constant, and find y. Well, here it's not going to be that super easy. Integration of y is going to give us y here. What is integral of 2 over t squared plus a constant dt? Well, guys, if you recall, we had integrals in calculus 5b, I think, which were looking like, sorry, oh, I'm writing down so much below the level that you can see. Very, very sorry. I even don't know what to do, because I was explaining stuff and writing it, and you probably did not see anything on the last line. So let me repeat last line. So for last line, I'm substituting v equals y prime, and y prime now equals 2 over t squared plus a constant, right? Integrating both sides, here is going to give me y, and here I'm going to get integral of 2 over t squared plus constant dt. So guys, you probably recall that if it's equal to 1, so it's actually 1 plus x squared dx, it's arctangent, right? If it equals negative 1, it's going to give you hyperbolic arctangent. So, well, it depends on the sign of a c constant. Well, give me a second. I'm going to consider or write down the answer using different signs for c, okay? Well, what I'm going to do, guys, I'll need to modify a little bit my expression. I want to deal with square roots. So what I'm going to do, guys, I'm going to represent C as a square root of C. That's a square of C. Well, a square of any arbitrary number. Imagine that I'm dealing with positive constant and C it's a square. Then I'm going to use a formula for arctangent, and I'm going to have 2 over C, and I'm going to have tangent inverse of T over C plus a constant, right? Plus additional constant. So I'm going to label this 1, and this one is going to be 2. So this is my solution when the constant C, this one, is positive, right? When the constant C over here is negative, I cannot kind of make it a square. So I'm going to write down, actually separate the minus from it, and then turn it into a square. If I do separate the minus, I'm going to have something like this. Y equals 2 over C tangent hyperbolic inverse T over C plus C2, C1, C1. This is going to solve the negative case. I'm supposed to put minus here also. I don't know, you probably don't remember the formulas. Maybe on the next page I'm going to provide you with the formulas, okay? So you can understand better how it works. But, well, again, depending on the sign of the constant. If constant here is positive, we can always represent it as a square of some other constant and get this solution. Okay, I'm going to write down that original constant is positive. So for positive constant, we are going to get this solution. If the constant is negative here, we can separate the minus and consider it as t squared minus positive constant again, and the constant is positive, you can use this one, that formula for it. But minus here is going to produce a different integral. It's going to be tangent hyperbolic. Or if you look at tables of integrals, you can also see a couple of lengths, because you can kind of decompose this into 2 fractions and kind of integrate. Well, I don't know which way is better, but there are going to be 2 solutions depending on the sign of a constant. Normally, guys, if somebody gives you initial value, you are going to have a certain constant, so you are not going to have 2 solutions. You're going to get either this solution or this solution depending on what is actual sign of a constant. But until you know initial conditions, you cannot tell which solution is going to work. Okay, and I think we can move to our next equation. It's going to be number two, equations with independent variable missing. Well, let me write down an equation and maybe you will see why independent variable is missing. Equation is going to look like this. You see, it's a second order equation, but there is no x or t. It's only y and y prime. I'm going to write down in parentheses no. Oh, sorry, guys. I moved it too far and you were not able to see nothing. Okay, our last part, equations with independent variable missing. Y second derivative equals f of y and first derivative of y. So there is no x or t in this equation. No independent variable. Only the function, derivative, and the second derivative. Well, how do we solve it? Method. Substitution. What substitution we are going to use? Derivative equals v of y. Well, interesting. This is not like our traditional v. That's a v. Traditional v was depending on x or t. Here it depends on the function. I'm going to label not x or t. Be careful. What does it mean? How it's going to affect everything? Well, let's differentiate and find the second derivative, because for equation we'll need a second derivative. So y prime, my second derivative, it's d. Well, I'm going to call variable t. d dt of y prime, or, sorry, my pen is dying. I'm going to use a different one. Just a second. We need to differentiate the expression for y prime by t, right? That's v, which depends on y, and y, which depends on t. So I'm going to have dv, dy, and dy, dt, right? Well, what is dy, dt? dy, dt, it's y prime, right? So I'm going to have dv, dy multiplied by y prime. And what is y prime? That's v. That's v. I'm going to write down v prime instead of this one, remembering that it's derivative not by t but by y. And instead of y prime, I'm going to write down v. So my expression is going to look like this. V prime multiplied by v. I'm copying the second derivative and the function. And the function is going to depend on y and on v. You see, it's again equation of the first order, and we can try to solve it. Let's consider example. Y by second derivative of y plus y prime squared equals 0. Well, let's do substitution. We're going to keep y. It's going to become our independent variable. Instead of y second derivative, I'm going to use what I calculated. Second derivative is v prime v. And over here, y prime, it's just my v, right? So it's v squared equals to 0. Well, I'm going to simplify this expression a little bit by taking v outside of both terms. So I'm going to get y v prime plus v equals to 0. Expression equals to 0 when either factor is equal to 0, right? So I can have v equals to 0 or this expression equals to 0. Well, let's consider first v equals to 0. I know that v is actually y prime, so y prime equals to 0 means that y equals to a constant. Okay, we'll solve the first one. The second one, number 2, we're going to have y v prime plus v equals 0. Here I can do separation of variables, right? dv dy by y equals negative y. So if I bring all my y's to this side and v to this side, maybe with minus, maybe without minus, but that's gonna give me dv over v minus dy over y. Not complicated, right? We're just going to have a couple of ln's if we integrate both sides. I'm going to integrate both sides, so I'm going to have ln of v equals minus ln of y. What does it mean? Don't forget about constant. I'm going to put e to the power, e to the power, e to the power. I mean, that's not going to be plus e to the power, but it's going to be multiplication actually here. So what I'm going to have? Well, here canceling, I'm going to have absolute value of v. Here I'm going to get e to the power of ln of absolute value of y to the power of negative 1, and here as usually e to the power of constant is going to produce me a new constant, just positive, right? I'm going to modify a little bit this expression. I'm going to get 1 over y, absolute value, constant here. Why it's 1 over y? Because it's negative 1. So this one is producing y, but if I apply negative 1, I'm going to put it in denominator. So what I'm having, v equals constant over y. Here my constant can be positive or negative because I kind of got rid of the absolute value. Here constant can be positive or negative. Can it be equal to 0? Let me see. If constant is equal to 0, then v is equal to 0, and we already kind of considered this case. So constant be equal to 0 is going to include actually the top case. Well, is it final answer? We know that v, it's actually y prime, right? So we're going to write down y prime equals constant over y. And we got another differential equation of the first order, which we'll need to solve here. It's kind of easy to solve by separation of variables. So it's dy over dt equals c over y. Let's separate variables. We're going to have dy multiplied by y. I'm moving this y over here. And dt moves towards c, dt. Integrating both sides is going to give me y squared over 2, sorry, not equal, but it's going to be ct, plus another constant c, so I'm going to label this 1 and this 2. Now I'm almost done. Do I need to solve it for y? Well, guys, if you wish, you can solve it for y but I don't think that it's like super important. You can leave your answer like this, so that can be your final answer. You can multiply everything by 2 and forget about this 2 because this is a constant, this is a constant. If you double them, they're still going to be constants. But otherwise, no, not much to simplify. Okay, now I want you to try something on your own. Use your new knowledge to solve something. Let me see if it's visible. Yes, it's still visible. So we are solving equation y second derivative plus y first derivative cube, and because there is no t or x, I want you to use my special substitution. I'm going to count to 3 and solve it myself, and I expect you to kind of at least try it. Okay. Okay, 1, 2, 3, and I'm going to do solution. Well, because it's like x and t missing, I'm going to make my substitution v equals y prime. And I'm going to substitute instead of second derivative v prime v, right? Remember from, where is my top? From over here. Okay, so what I have, v prime v plus y, and instead of v prime I put v cube equals 0. Well, here I'm going to kind of put v outside and have v prime here plus y v square equals to 0. And again, there are two solutions, v equals 0 and this part equals to 0. V equals 0 is going to give us y equals a constant, right? We remember that v is a derivative, so y equals constant. This part equals 0 is going to give us differential equation, unfortunately. I'm going to write it down here, but then I'll need to move to next page. You still can see it, right? Plus y v square equals to 0. Okay, so what we have, dv dy, remember that v does not depend on t or x, depends on y. It's minus y v square. Well, we can separate variables here, right? We can put dv over v square here and minus y dy on this side and integrate both sides of this equation to get negative v over here, negative 1 over v, and minus y square over 2 plus a constant. So now let's solve for v. I suggest to multiply by negative 1 as well. So v is going to be equal to 1 over, I flip over this fraction, y square over 2 plus c. Why do I keep plus c if I multiply by negative 1? Well, minus c or plus c, because c is arbitrary constant, does not matter. Now I'm going to recall that v is not our function which we are looking for. We are looking for y prime. We remember that y prime equals v, right? So actually we are going to get another differential equation, y prime equals 1 over y squared over 2 plus a constant. Now we are going to solve this differential equation. You see, it's kind of, we solved one first order differential equation before, right? We got our solution, and then we are solving second one. So actually we are solving two differential equations to resolve each derivative. So now what we have over here, we can solve by separating variables. We do have dy over dt, right over here, equals 1 over y squared over 2 plus a constant. I'm going to multiply everything by the denominator, put it on this side, and put dt over here and integrate. y squared over 2 plus a constant dy, and on this side I have just 1 dt. Put the integral on both sides of this equation. Well, y squared over 2 is going to give me y cubed over 6, right, over 2 and over 3, plus cy equals t plus another c. Well, this c comes from my first equation. This second c comes from my second. So I'm going to put labels 1 and 2 here to show that there are two different c's. Should not be mixed. Now, guys, what I'm going to do, I'm going to move everything besides c2 on this side of this equation, or you can even leave it like as it is, because you won't be able to solve it. That's a cubic equation for y. I don't know, actually, maybe makes sense to kind of write it down. Y cubed over 6 plus c1y minus t equals c2. Well, there is basically no difference between these two answers, but that's the final answer. Don't forget that when you get v, that's not final answer. We're supposed to continue and find what is going to happen with y, actually. Y prime is going to just produce a new equation. Okay, that's all about missing independent variable. By the way, whenever you label independent variable like t or x, that's your choice, because when equation does not have it and you don't have any clue how to label it, well, you can choose a name.